Hi everyone. So after introducing the idea of hypothesis testing in the context of the illustrative example of Paul the octopus predicting matches of the 2010 soccer World Cup, we're gonna move now to a more applied example that is actually connected to some of the analysis that we talked about in previous weeks. And this is focused on hypothesis testing in the context of proportions. And specifically, what we're going to look at is hypotheses where we want to reject a null hypothesis about a true population proportion or true population proportion being equal to some value. So, for example, in the context of presidential support for presidential candidates, the support for one particular candidate being larger or equal to, for example, 50%, right? So the hypotheses here are or there are two hypotheses again, as always in this framework. We have a null hypothesis that the true population proportion p is equal to p naught or p0, which in our case could be, for example, 50%, or it could be 0%, or whatever. But in the case that we're going to look at, since we're going to look at it in the context of election polling, it's going to be 50%. And our alternative hypothesis in this case now will be that p is not equal to p0. So p, the true population proportion, is not equal to 50%. It could be larger, it could be smaller. We're agnostic as to whether it's larger or smaller. We're just saying the alternative hypothesis is that it's not equal to that hypothesized or null hypothesis population value. Okay. Our test statistic is, of course, xn bar. That's the average proportion in our sample, where xn is, of course, a dichotomous variable that takes values of 0 or 1. So the average sample average of that variable is the proportion, is equal to the proportion, or can be interpreted as a proportion, right? So now under the null, and we talked about this in the context of computing confidence intervals for proportions in the context of polling or election polling results, we can say that under the null, where p is, assuming that p is equal to p0, so 50% support for one candidate, for example, by the central limit theorem, we can say that the z-score, so the deviation between x bar and the true population value p0, so that's x bar minus p0, divided by the standard deviation, or that's the standard deviation of the sampling distribution, or the standard error, which is of course equal to p0 times 1 minus p0 divided by n. Is distributed according to a normal distribution with mean 0 and standard deviation 1. So it is distributed according to a standard normal distribution, right? That's one way of how we kind of characterize the central limit theorem. Of course, in some cases we talked about just x bar being normally distributed with a certain mean and a certain standard deviation, but here we're looking at x bar, which is one, on the one hand it's mean centered, so we subtract the mean, so that means or we subtract the true population mean, so to speak. So that means the sampling distribution is centered at 0, so the mean here is 0. And we're dividing by the standard error, by the standard deviation of the sampling distribution. So that means it's rescaled such that the this kind of z-score is then distributed according to a standard normal distribution with mean 0, standard deviation of 1. And of course that means that we can directly make probability statements about observing a certain z-score in our sample, and how likely it is to observe that z-score in that specific sample under the assumption that the null hypothesis is true, under the assumption that P0 is actually the true population proportion that we're interested in. Okay? So, of course, similar to our previous discussions, the question, of course, is whether the z-score that we observe for our specific sample is unusual under the null, under the assumption that the null hypothesis is true and that the true population proportion is equal to P0. Right? And as we said before, we reject the null if our z-score is larger than our critical value, and we retain the null. We fail to reject the null if our z-score, or the absolute value of the z-score, is smaller or equal to our critical value. Okay? Note here we're looking at the absolute value because our alternative hypothesis is just that P is not equal to P0. It might be larger, it might be smaller. We are agnostic as to whether it's smaller or larger. We're just testing against the null of P being equal to P0, and it can be either smaller or larger than that value. Okay. Of course, the level of this test is essentially our alpha. That's the probability of rejecting the null hypothesis under the assumption that the null hypothesis was true. Okay, so that's, in other words, the probability of making a false negative. The null hypothesis is true, but we're rejecting the null hypothesis falsely. Okay, and this is very essentially directly connected to the way we thought about confidence intervals, right? We already computed confidence intervals for specific critical values and for specific levels, like 95% confidence intervals or 90% confidence intervals, right? And this is kind of equivalent. Rejecting the null hypothesis for a given confidence level is essentially equivalent of P0 being either included or not included in the confidence interval for that specific level, right? So in other words, if we engage in a hypothesis test with a rejection level of 0.05, so that's 5% significance, that is equivalent of computing the confidence interval for the 5% confidence level and examining whether zero, or whether, I should say, whether that P0, whether that null hypothesis population parameter is included in the confidence interval or not. Okay. Another thing I should mention is that when xi is normally distributed, and this goes back to the previous week, we can use the t statistic and the t distribution without relying on the central limit theorem and obtain the critical value using the student's t distribution. But if we have a large number of observations, we can rely on the central limit theorem and basically rely on the normal distribution. In practice, people often just rely on the t distribution because essentially for large sample sizes, the t distribution approaches the normal distribution anyhow, so we don't really have to worry about that. And if anything, the t distribution is the more conservative choice in that regard, right? But the key point here that I want to emphasize is this duality between the hypothesis test and rejecting the null hypothesis at that given level, right? And so if you kind of go back through that logic of the interpretation of the 95% confidence interval, right? We said, when we went through the interpretation of the confidence interval, we said that the 95% confidence interval doesn't mean that we have a 95% chance that the true value is within that confidence interval, right? But what we said was that under repeated sampling, 95% of those confidence intervals would include that would include the true value across repeated data generating processes, right? And we had the simulated repeated sampling scenario where we computed multiple confidence intervals and saw that across 100 samples, approximately 95 would basically exclude the confidence, exclude the true value. 95 would include the true value, and 5 wouldn't include the true value for the 95% confidence interval, right? And so that's basically equivalent of rejecting the null hypothesis that the true population parameter is equal to or that the null hypothesis is true and the true population parameter is equal to p0 at that given confidence level, right? So if we're at a point where we have one sample, we construct a confidence interval, and that confidence interval does not include the true the p0 that is assumed to be the population parameter as part of our null hypothesis right here, then that means that assuming the null hypothesis is true, right, we only have a in this case, for example, 5% chance that that our confidence interval would not include that specific true population parameter under the null, right? And so therefore, given that level, we would then reject the null hypothesis because we think it's unlikely that just by chance we would find a sample, construct a confidence interval that then wouldn't include the true population value, right? So it's important to kind of go through that logic and see how the 95% confidence interval and rejecting a null hypothesis at a level of 0.05 significance is equivalent in this repeated sampling sense that we talked about. Okay. So this brings us back to, directly brings us to the main key point that is incredibly important and incredibly error prone, even among people who spend years, or social scientists who spend years kind of studying or using statistics, which is interpreting or correctly interpreting p-values. Okay, and this kind of goes back and is again related to this interpretation of the confidence intervals that we now talked about for quite a bit, right? The p-value is the probability under assuming that the null hypothesis was true of observing a value of the test statistic at least as extreme as its observed value. Okay, so we can think about this in the example that I just showed you in the context of population proportions. We looked at this from a in the context of a two-sided alternative hypothesis. So we said we look at a null hypothesis of p being equal to p0. That's the population proportion that we looked at. And the alternative hypothesis is simply that p is not equal to p0, right? And then the p-value is essentially the probability of z being larger than our observed z value or smaller than the negative observed z value, right? So we have to look at both the probability of being larger and smaller than the observed value, essentially. Okay. We can also look at one-sided alternative hypotheses. Here, the null hypothesis is the same, so that's p is equal to p0, and our alternative hypothesis is either that p is larger than p0 or that p is smaller than p0. So we're not looking at p, the proportion being just not equal to the null hypothesis population proportion, but it has to be only larger or only smaller. And of course then we're only looking at the probability of the z score that we observe being smaller than the critical value or larger than the critical value. Okay, so that's the one-sided alternative hypothesis, right? When it comes to interpreting these p-values, a smaller p-value represents stronger evidence against our null hypothesis, right? Because again, go through the underlying logic. The p-value gives you the probability, assuming the null hypothesis was true, of observing the test statistic that we see in our single sample, that is as extreme as that observed test statistic, or strong, or more extreme, right? So if the probability of observing such a test statistic in our single sample is incredibly small, right, then that suggests that the null hypothesis is unlikely to be true, right? So a smaller p-value presents stronger evidence against our null hypothesis, right? A p-value of less than alpha, which is our kind of cutoff critical value for statistical significance. So a p-value less than alpha indicates statistical significance, right? So this is when we talk about like a 0.05 significance or 0.01 significance and things like that, right? In regression tables, you often see stars indicating significance at different levels, and those are the alpha levels in that context, essentially, okay? What is important to emphasize in this context, going through this interpretation of p-values, is that the p-value does not give you the probability that the null hypothesis is true or the alternative hypothesis is false, right? It is just a measure of the likelihood of observing our sample test statistic under the assumption that the null hypothesis is true. It does not give us the probability that the null hypothesis is true in itself, or that the alternative hypothesis is false, right? So, in other words, if we find if we do a hypothesis test and we find an insignificant result, we cannot conclude from that the null hypothesis is necessarily true. We can only conclude from that we fail to reject the null hypothesis, right? That's for an insignificant result. If we have and at the same time, if we have an insignificant result, we cannot necessarily conclude that the alternative hypothesis is false. Again, all we can say is that we fail to reject the null hypothesis if the test is significant, if the test is not significant, and if it is significant, we do reject the null hypothesis. Okay, that's all the p-value is telling us, essentially. Okay. And then another point, even beyond the interpretation of kind of statistical significance and the p-value, it's important to keep in mind that statistical significance itself does not necessarily imply scientific significance or kind of substantive significance, right? So that's why when we interpret regression results, we always want to look at also the actual like substantive effect sizes, in order to kind of get a full understanding of the meaningfulness of the effects that we observe. The underlying reason here is, of course, that statistical significance is in of itself a function of the sample size, right? The larger your sample, the easier it will be to reject null hypothesis, right? So basically, essentially, you can reject any null hypothesis if you just have a sample that is large enough, so your estimates gets more and more and more precise, and then ultimately you'll be able to reject any null hypothesis, right? So in order to kind of don't make the mistake of just rejecting null hypotheses based on or interpreting rejected null hypothesis necessarily as like substantively interesting and important results, we have to look at the full picture. We have to look at effect sizes and so on, and also have to take into account sample sizes and so on to really look at the full picture. Okay. All right. So I talked about hypothesis testing in the context of these proportions, and so we should of course go back to our polling examples that we talked about in previous weeks to kind of go through these examples quickly, okay? And I'm just gonna show them really quickly, and feel free to go through those examples by hand and pause the video. We talked about Obama's approval rate in the context. Now I'm not sure whether this was in the context of the 2012 election or the 2008 re-election. But essentially, our null hypothesis here is, of course, that the approval rate is just 0.5 or 50% approval. We look at this from a two-sided test, so we have the alternative hypothesis that p is not equal to 0.5. We want to test this null hypothesis using an alpha level of 0.05, so 5% significance level. Our xn bar, that's our sample average, that which we compute based on a sample with 1,500 respondents, is 0.45. So now we can compute our test statistic, which is the z-score for that specific sample, which is the deviation between our sample mean and the true population mean, assuming that the null hypothesis was true, so that's 0.45 minus 0.5, divided by the standard deviation, which is just 0.5 times 0.5 divided by 1,500, so that's the variance divided by the sample size, and that's equal to 3.87. And now the question is, how does this, and under the null hypothesis, as we said, given the central limit theorem, this z-score is distributed according to a standard normal distribution. So we can directly look up how likely it is to observe kind of a value of 3.87, assuming a sampling distribution that follows a standard normal distribution with mean 0 and standard deviation 1, where our z-score is, if we assume a 5% significance level, is of course 1.96. So just by looking at these two different values, we can say that this z-score that we observe is larger than 1.96. So we're rejecting the null hypothesis at the 5% significance level. Okay, we can also directly compute the p-value, which is the probability itself of observing our specific test statistic under the assumption that the null hypothesis was true. And in order to do that, we can just use the p-norm command and plug in the equation that we just derived. And we see that the p-value, of course, this is a two-sided test, so we have to look at the probability of being larger or equal to that z value on both sides. So we just multiply this by 2. And we see the p-value is very small. It's just 0.0001. So again, it's a very small, under the assumption that the true population approval rate was 50%, it is very unlikely that we would observe a sample of size 1,500 where the average approval rate was 0.45. So we reject the null hypothesis at the 5% level. Okay. Here's another example using or focused on Obama's margin of victory. Here we have a null hypothesis where the margin of victory is equal to 0, and the alternative hypothesis, now this is a one-sided test, and we have an alternative hypothesis where delta, the margin of victory, is larger than 0. Now, just to switch things up a little bit, we look at a alpha 0.1, so 10% significance level, and our delta hat is 0.03, right? So the observed margin of victory is just 3 percentage points in our sample of 1,200 respondents. Okay. We just go through the same logic. We compute our z-score based on that sample. Again, that is 0.03 minus 0, because the null hypothesis is that the true margin of victory is just equal to 0, divided by our estimate of the standard error, which is equal to 1.04. And assuming a 10% significance level where the critical value is 1.28, we see that we fail to reject the null hypothesis because our observed z-score is smaller than our critical value of 1.28. Again, we can directly compute the p-value based on our observed z-value in our sample using the p-norm command. Here we're using the lower tail equals false argument because we're looking at a one-sided test, and we want the probability of observing a value larger than the z-score that we observe. So that means lower tail is equal to false, and we see the p-value is 0.149. So obviously that's larger than our significance level of 0.1 that we tried to achieve. So we're failing to reject the null hypothesis. Okay. The last example that I want to go back to is our social pressure experiment that we talked about a bunch in previous weeks, where again we compared turnout rates between a control group and a treatment group in the context of Michigan primaries, I believe in 2006. Okay, and if you go back to this example, we observed a treatment average or an average turnout rate in the treatment group of 37% and an average turnout rate in the control group of 30%. Okay, and now the question is, of course, whether these differences are actually significantly different from each other. And note that this is a different example from the previous examples that I just went through, where we basically look at one sample and compare our sample against the null hypothesis of the population parameter being equal to some value. Here, we're looking at two different samples, and we want to examine whether those two samples are significantly different from each other in order to estimate the average treatment effect of our intervention. Okay, so we have two different sample sizes, we have two different sample averages. We're looking at the difference between those two. Okay. So the sample size in the treatment group was 360 voters, or 360 registered people who were registered to vote, and we looked at actual turnout. And in the control group, we have 1,890 people. Okay. The average treatment effect, of course, is the difference between xt bar and xc bar, and that's just 0.07. Okay, the standard error of that average treatment effect is just the variance of xt bar plus the variance of xc bar, making the assumption that xt bar and xc bar are not correlated with each other. So that means that the variance of the sum or the subtraction of those two values is just equal to the sum of the variances. So the sum of the the individual variances are, of course, xt bar times 1 minus xt bar divided by nt, and same for the control group. And we add them together and we take the square root in order to compute the standard error. If we plug in those values, we get a standard error for this average treatment effect of 0.028. Okay. Now we can compute the confidence intervals, and we actually did this in a previous video, but just to reiterate, in order to compute the confidence intervals, we select a critical value. For example, we want the 95% confidence intervals here, and we take our average treatment effect in our sample or in our experiment, and subtract and add the standard error times our critical value, assuming that confidence level, in order to compute the confidence intervals. This here, of course, should be a plus rather than a minus. We subtract in one case and we add in the other case. Okay, the confidence interval that we compute is 0.016 and 0.124, which of course does not include 0. So if the null hypothesis is that there's no difference between the treatment group and the control group, we can already say, based on the 95% confidence interval, that we would reject that null hypothesis at a 95 or at a 5% significance level, because the 95% confidence interval does not include 0. Okay. So this is an example, as I mentioned, of a two-sample test, which where the null hypothesis is the true population proportion in the treatment group is equal to the true population proportion in the control group, and the alternative hypothesis is that they're not equal to each other. Okay. Um, um, so based on that, we can make a couple of additional um, uh, a couple of additional computations. First, the first thing we want to do is we want to compute the common mean, which we will just assume in order to compute our standard error under the null hypothesis, right? Because under the null hypothesis, we need to compute a standard error under the null hypothesis, and in order to compute that standard error, we need a true population proportion. The true population proportion, or our estimate for the true population proportion, is that P is equal to the common mean, which is just the weighted average of xt bar and xc bar, each weighted by their respective sample sizes. So we have xt bar times nt plus xc bar times nc divided by nt plus nc. So you could think of this as the weighted average of the turnout rates in the treatment group and control group weighted by each respective sample size. So that's an average turnout rate of 0.311, right? So we assume that this is the common mean under the null hypothesis, that pt and pc are actually equal in the population. Okay. The standard error then under this null hypothesis is again assuming that xt and xc are xt and xc are not correlated, is of course the sum of those two variances, and I'm just realizing that I'm kind of repeating the information up here, but of course if we plug in the p-values here, now assuming kind of the common mean p, we get a standard error under the null of 0.027. This is assuming kind of a common standard a common standard error under the null, essentially. Okay. Then based on the standard error and based on this common mean, we can specify a reference distribution for xt bar minus xc bar. So the difference between xt and xc. And that difference under the null hypothesis follows a normal distribution with mean 0, of course, because we are assuming that the difference between that pt and pc are equal, so the difference between the two is equal to 0, and a standard deviation of 0.027, or a variance of 0.027 square, essentially. Okay. Then based on this reference distribution and the observed difference of 0.07 that we actually see, we can say that the p-value is equal to 2 times, again this is a two-sided test, p norm for 0.07, so observing a value larger or equal to 0.07 for a for a normal distribution with standard error of 0.027, which we specified here, and a mean of 0. And if we run this in R, the result is about 0.005 so that times 2 is 0.010. So in other words, based on the observed difference between treatment and control, we reject the null hypothesis that the treatment and control group have the same turnout rate in the population at a 0.05 significance level. Okay. Okay. All right. That concludes our discussion of basic hypothesis test. In the next video, I'm going to talk briefly about error and or different types of error in hypothesis tests and the power of hypothesis tests. And then in the last video, I'm going to talk about uncertainty in the context of regression models.